What is it?
Something was my turn. Right? Okay, awesome. I don't often speak with the mic, so if something doesn't work out, let me know. We'll try to figure it out. All right, so this talk is about a recap of CVPR 17. 2 words about me. I'm Simon. I work at Instrumental. Instrumental is like a small startup. We're doing AI for manufacturing. Not going to talk much about it, but if you're ever interested in like challenges of how to bring machine learning and AI to the manufacturing process, like got stories, would like to hear stories. All right, so CVPR. So CVPR is computer vision and pattern recognition. It's the one of the top conference, if not the top conference about computer vision in the world. There's this cool graph that it's like now it's accustomed to show of attendance over the years. And this graph, you can see that it ends at 15, at 2,500. 17 was 5,000. So it keeps going like exponentially up, like a lot of the conferences where deep learning is anything in it. And you can see how it's traditional computer vision, then some machine learning stuff happened, and then deep learning appeared, and it keeps going and going up. One thing I wanted to say is, I'm not sure if a lot of you were at the kind of academic conferences, but they have this thing called poster format, which works amazingly well. And the way it works is after there's like so-called oral presentations where people talk about their work, there's like this huge holes where authors of the papers stand in front of them, and you can come in and talk, and they'll always happy to give you like a very short overview. And even like the authors of the top papers sit there, like stand there for hours, and like never stop at giving overview for like 5 minutes for the 100th time for anyone who comes by. And you can ask questions and get their attention. And this is just works amazingly well. It's like a massive download to your brain of everything that's happening in the space in a very like great and interactive manner. And I think like half of the value of the conference is this format. The other half is, of course, parties at the conference. So CVPR is the computer vision conference, and it's still like multi-track and huge, and it's impossible for one person to get everything that's happening there. This is around maybe between half or 30% of CVPR closely related to like deep learning and more specifically working with images. There's another half of, there's like kind of, you feel that there's this world separation of people doing more like traditional computer vision and solving things like real-time localization and so-called SLAM, and discussing like the new physical optics and new cameras and stuff like this. And there's this kind of parallel world of you know, convolutional neural networks, deep learning, and like other ML-related stuff. And you can kind of feel that there's not just tension, but people are like looking at each other like this. It's a little bit. All right, so this is kind of the general observation. And of course, there's like a lot of industry, and this is one of the example of the conferences that were like small academia type of get-together that industry took over, and now like all of the self-driving companies that you can think of are like there and presenting. And you learn about new companies that starting to do self-driving. There's a question? Yes, yeah, it's a different city every year. This year was in Honolulu. Next year, I don't remember. I want to say Australia, but I'll travel. Hmm? Oh yes, yes, yeah. Thank you. Yeah, ICML is in Sydney. Yeah. All right. So the main idea of the talk is to go kind of general themes on the conference, and for each of them, try to get into a couple of interesting papers in the details. Now, I don't know about kind of what's it's hard to gauge how deep you want to go and what kind of detail to cover or not cover. So if a particular paper catches your eye and you feel that this is too shallow or does not talk about the necessary background, please talk to me after this. We have plenty of time to hang out and to ask questions. I'm really happy to dive into detail and do basically the same overview as what people do in the conference. So one big theme which goes in many formats is how do we need less labeled data to train our models. Everyone knows that, like, to train big deep learning models, you need a lot of labeled data, which is expensive to gather, to combine the world. And is there a way we can do something to need less of it? The exciting development this year, which didn't happen before, is trying to use simulated data. Right? If you have a simulation or something that could generate data on demand and able to train on it, this would be like a miracle, right? Because you can scale it as much as you want. You instantly start getting like orders of magnitude more data. The question is how to do it and how to, like, all of this synthetic data by definition is different. And this is best paper award from Apple. Apple is doing papers now. Good job, Russell Lipidino. And the idea here is using so-called adversarial networks to make synthetic images look more real. So their setting is, say you want to train a system that does gaze direction detection, right? Like there's a photo and you want to predict where is the eye looking. And you have a simulator and you have no labeled real data at all. You have a lot of unlabeled pictures of real eyes, but you don't know where they're looking. You have no labeled data whatsoever. But you have a system that is able to generate those non-realistic looking images where you know exactly where the eye is looking because you generated them. This is one of the parameters. And the idea is to train a special network that's called a refiner that would take this image and produce something more realistic. And the way this adversarial setting works is there's another network trained at the same time that receives both pairs of this and this, and needs to be able to say what's real and what's refined. So like in the beginning, refiner generates some garbage because it's like not initialized, and it's really easy for the discriminator to tell which is real and what is garbage. But then you start training it, and refiner learns to produce more and more and more realistic images based on this until it can't, like, discriminator cannot distinguish them apart, and at this point your training converged. This is like a very standard adversarial network setup, but the exciting thing is now, as a result, you have a model that can take synthetic, produce real, where you know the gaze direction. The necessary trick here is how to stimulate refiner to still make it the same eye direction, right? Like technically, since it's a powerful model, it can learn to transform it in any way possible. It does not really have to maintain the eye direction. And to do this, they have a special loss that, in addition to like fooling the discriminator, refiner should minimize difference in pixels between this pixel, this image, and this image. So moving the eye around is a very expensive operation because you need to change a lot of pixels. So what it learns to do is to just add some noise or some shape or features that are indistinguishable from the real. Does that make sense? Yeah, there's a question. Louder, please. Ah. Thankfully, I'm not the responsible person for Wi-Fi. All right, and then they train on this data, on this refined data. And in other tasks where they have a little labeled data, so the graphs here are the higher the graph, the better, and they can show that on the refined data that you can generate 3x of really easily. There's a lift. So this data is actually useful for training, and that's now's a good time to go home. That it's actually using GANs synthetic images helps, which is like before that we used GANs to generate pretty pictures, right? There was not clear idea how to use it, and now there's a practical use, which is awesome. Another setting where we're trying to train models with less labeled data is we have a small labeled data set, which is expensive to get, but really large unlabeled data set. And we'd like to use it somehow for the training. And the cool paper I want to mention, the results are on NIST, as you see, so it's like less cool, but I think that the idea is really interesting. And the idea is you have a small labeled data set and a very large unlabeled. And in addition to just training on labeled, you have an additional constraint that lets you use unlabeled data to produce better results. And here's how you do it. So you, in a single batch during the training, you include labeled and unlabeled data together. And so CNN produced some embeddings for each of those images in a batch, which later, for this one, you just train a classifier. But you have an additional loss that basically says this. So imagine that for an embedding, there's a random process that goes from one label in a sample in a labeled data to the unlabeled one based on the proximity of the embeddings. So basically, like for this one, you're like, okay, which of these embeddings are most similar to me? And I'm going to go proportional to the probability, with the probability according to how close they are. And from wherever I end up, I do the same thing for the hopback. And the idea is that if all of your embeddings are good, you expect that if you hop here and back, you'll end up in the same class. So if the model trains well, from 4, it's likely that you'll jump another 4, and back you'll jump to the instance of the same class. And if you didn't do this, that's bad. And if you did, and if you end up with the same class, that's good. And this is like kind of an additional regularization prior that stimulates using the diversity of the unlabeled data to figure out what class they are, and so they're aligned with the labeled data. And they have cool visualizations on NIST. I'm not sure if you see it, but basically, so A is the labeled part, B is unlabeled, and in the beginning, when you just starting training, you can see how it goes. It's somewhat random, right? Sometimes it's like 0 to 0, but like sometimes 2 goes to 7, 7 goes somewhere else. It's like all over the place. And after the training converges, it's like very straight up. 6s go to 6s, back to 6s. 4s go to 4s, straight back to 4s. And they did demonstrate in evaluation that it does help. It does help the final results as well, which I think is like a really cool idea. Right. Make sense? All right. There's a minor paper related to this that tries to compensate for the noise in your ground truth labels, which is always present. They try to estimate and compensate for it. Not going to go into details. Just wanted to mention if for someone this is a practical problem. Now, the other large part of using the data, like using less data, is so-called semi-supervised learning. And what this means is you're trying to fish for data that's there in your data set implicitly, but not explicitly. What do I mean by that? So here's one example. And the setting here is, of course, there's a lot of research for self-driving cars. And this is, you're trying to make a network that takes an image and produces a depth map, which is single image. No stereo, no nothing. One image produced depth. And people are able to do this by looking at the cues in the background and everything else. Let's see if the network can do it. And you have some data. You have some sparse ground truths from LiDAR or something like this. But the problem with LiDAR, it doesn't highlight every pixel. It's like here it seems like a lot, but it's like every 100th pixel or something like this. So you have depth value for some of those, but not for everything. But what you have is a stereo image during the training time. And the way you're able to do this, you're basically saying, okay, so if the first network predicts some depth, I can use this to try to reconstruct the second image. And it's better be close to the actual second image here. And they have two losses. One is supervised for the pixels where you have data should be closed, and unsupervised is if I apply my prediction to my source to warp it based on depth, it should be really close to a stereo one. And it turns out that you can express this warping as a differential function, so you can train the whole thing end to end. So this data, like the depth data, was not explicitly available, but the fact that since you had stereo image, you can infer it and make it as a constraint for training the network. Another example in this section is even more extreme, finding things that do not exist in training data at all. And the setting here is, imagine you have images of the pictures of the streets from the street view, and sometimes people forget to add a ramp here, right? It exists here, but on that side of the intersection, people didn't do it. And you have those ramps labeled as the ones that exist, and you're trying to find the ones that people forgot, and you don't have any data about where people forgot to put a ramp, right? You only have the data about where they exist. How can you do this, right? So you want to be able to find detector that finds missing ramps when you have no information about missing ramps. And their idea is, well, first you detect, you build an object detector for ramps, and you have train another network that tries to figure out, should the ramp technically be there based on context? So based on the stuff around, this looks like an intersection, there should be a ramp. And you basically try to find places where based on context, it should be there, but our detector can't find it. This means it was missed. So the key part is, how do you build this context time? They have a cool trick. So the train network with two losses. One is, so you get the network receives an image where this ramp thing is black, so you don't know whether it's there or not, and tries to detect whether ramp is there or not. And there's a parallel, the same network, where it receives image without the black, so it sees what's there, but its result should be very close to the result of the first pass. So you train the network to ignore this information. You train a network that even when it sees it, it should predict the same way as if it didn't see it, right? And this trains the network to predict the existence of the ramp based not on the ramp itself, but by the context around it. And if this prediction disagrees with another model that just learned to predict ramps, this means someone forgot to do it. And there's another example of, you have some data, but you can twist it in an interesting way to find new type of data that was not available to you directly before. Finally, transfer learning. So this is a technique, transfer learning is a technique that everyone uses, and this is like a starting point for everything. If you're training a specialized network for, say, image recognition, you start with the network that's pre-trained on a large data set with a generic task, and you fine-tune it to your particular problem. So the setting here is like you have the big source data set and the small target data set. And usually what people do is basically only take the network pre-trained here and train only on the target. And there's this approach proposes a way to do this more efficiently. And the way they propose to do it is basically have a mix and find some items in a huge source data set that are similar to the one you want to be training on, and train on them together in a single network where there are two classifiers, one for source, one for target. So basically, when you're fine-tuning, you have an additional constraint that it also shouldn't forget how to classify a large amount of the previous data that's similar to you. Does that make sense? And they also show that there's benefit in doing so. Go ahead.
I guess a lot of ways when you reframe the final layer and you forget the classification of the original set, right? Like, for example, we create 1,000 classes without two classifiers of two classes.
Yep.
And it adds a value to, reduces the noise in that sense, right? So what they talk about, like, if you actually retrain it for 1,002 now, does that not increase the noise about classifying?
Yeah, so they have two classifiers. So in this sense, they'll still have 1,000 or whatever classes that are being close to the new data set that you're doing, and have two. And I think they mix the batches so it's like still half and half in like during the training. So that this 1,000 will not completely overweight the two because the amount of sample is somewhat similar. And the proximity metric for them is some pre-trained CNN. They look at first layer features, and if they're close, this means they'll add the source sample into the training set. Which is interesting because like this is something super common, and we do this every day. And there's a simple way of making it better by using the source class. Oh, what happened to my? Okay, that's not supposed to happen. Dropbox, something to work on. Guess the picture is not important here. Like the one thing I wanted to mention, before machine learning and exploring, I did game development and real-time graphics, and there's work where people created a fully differentiable render. The task here is you go from face. You want to reconstruct the 3D geometry of the face based on just a single photo, and the network proposes some 3D structure of the face, and in between the network they have an actual renderer that renders something close to a photo based on proposed 3D structure, and their loss is if you render it, it should be close to source photo. And for this, they have to come up with like a 3D rendering code that's fully differentiable so you can insert in a neural network. That's like an amazing feat of engineering that I thought was a highlight. Another similar thing where it's the similar paper where they simplified this a lot, so it's not the full renderer, but doing something similar. All right. So the next theme is the theme that we usually expect from the conferences: architectural improvements on existing tasks. One thing, I don't like this. What's up with this internet business? Let me try to refresh. Sorry, everyone. Is it making sense so far? Good pace, good amount of detail? Where are my pictures? Yeah. All right. So this is also best paper work. This is basically every year brings new architectural innovations in the field of deep learning. This is what we can kind of check in for this year. This is what we as a team came up with this year. And it's called DenseNet, best paper work from Facebook. And the intuition here is the usual, this is convolutional neural network. We're solving a classification task, trying to make things better with a better architecture. So quick recap on ResNets. This is a picture from the ResNet papers, residual networks. And the innovation of ResNet, they added so-called shortcut connections, where instead of just going through the layers, there's a shortcut connection that they just plus with the output that lets kind of each layer only learn the delta between the previous feature representation as opposed to learning from scratch, which really helped the learning process. And there's different interpretations why. One common interpretation is that this architecture facilitates the gradient flow. What this means is when you think about how gradient flows back in this network, those connections have like a direct link for gradient from the beginning to every layer of the network. And this facilitates learning a lot. Now, DenseNet is trying to take this idea and run as far away with it as possible, well, reasonably possible. So their basic block looks like this. This is the input, and there's like basically a couple of convolutional blocks in the middle, and every block here receives input from all of the previous blocks. So the second one only receives from the first. The third one receives both second and the first, It's like it goes like this. So the final one receives input from all of the previous layers. And this means that there's just a lot of ways for gradient to flow between them, not just one pathway, but like n squared number of pathways. And of course, this only works if they're the same resolution. So at some point, they need to pool. So their architecture is their input. There's this block of 5, pooling, another block of 5, another block of 5, and the result. And the interesting thing is, the paper these days, no paper can really show improvement on the state-of-the-art results. State-of-the-art results produced with ensemble of many powerful models. So asking for like people who introduce a new architecture to really replicate all that is really hard. So they showed improvement on the single model performance. But the latest ImageNet results came in where there was a substantial, I think 25% or something like this improvement over previous, and they use a lot of dense nets in their ensemble. So like other people perform the work of actually kind of productizing this for the ImageNet competition, and it seems that it's working. So this is the best we got. Another architectural innovation I want to talk that I think has a lot of the practical impact is so-called polygon RNN. And the idea here is you solve a segmentation task. And usually the way people solve segmentation tasks is they classify each pixel, right? And this is like instance segmentation, so you take a crop, and your goal is to, for every pixel, say, is it like that instance or this or not? And they changed the formulation that instead of predicting for every pixel, they predict a sequence of points that you connect with a polygon, and that's your segmentation. The interesting detail here is the way people produce ground truth for these masks is always something like this. No one in their mind really like looks at every pixel and selects the class. It's just too much work. So there are tools like this. And the cool thing about their architecture is it's like built in to learn from corrections. And what this means is if the model produced some outline and human moves one of the points to a better location, it's able to take this information and recompute all other points based on this. And this has, I think, like a very practical impact in software, because the way to get data from user action when you're preventing, like when you're producing some prediction, is by letting users to correct it. But if nothing changed based on the correction, it's very slow user feedback, so like it's not really encouraging people to do something because you're not going to be able to correct. And to correct, you really need to retrain the whole model. It takes a lot of resources, a lot of time, and stuff like this. So delivering right on time correction is really hard. And this architecture learns to do this without retraining the model, which I think is exciting. This approach could be used in a lot of the software products. The way they do this is basically a combination of CNN and RNN. Meaning, so they first extract CNN features based on like VGG architecture for some reason, and then they feed this into LSTM that for every point, for every step, produces like a feature map where with a field of where should they put the point, and then they sample from it, and the next layer receives what is the point that was sampled from this little grid. And the way training works, like the way correction works, is if you corrected a particular point, they would just override what the next layer will receive based on how it was corrected by human. So all of the follow-up layers will react on this and use this as as a correction mechanism. And during the training, they train the network on this scenario. So during the training, network sees instances where this point is moved to somewhere else, not where it was predicted before, and is supposed to produce correct labels for the follow-up steps. Which is an interesting way of kind of reformulating the task so it allows for human feedback. All right, final big group is, it's a computer vision conference. So people kind of discover deep learning and are applying them to all computer vision tasks under the sun. And sometimes it requires new architectural changes, but you can see that this deep learning becomes one of the building blocks that gets applied to all of the tasks in the world, at least in computer vision space. And I think computer vision is kind of a couple of years kind of in front of all of the other fields where deep learning made an impact, just because deep learning happened first in the computer vision space. So we should be expecting to see all of the other practical engineering fields to be overtaken by this in like coming years. One necessary architecture change is when you want to work with graphs or point clouds. So the task here is you have just a set of points or point cloud, as it's called in computer vision, and you want to either classify or segment or do a semantic segmentation when there's like a point cloud, and you want to say what's the chair, what's the wall, what's the table and the floor and stuff like that. So the challenge of using standard architectures for this is that the set of points is unsorted and could be rotated in any way. And unsorted is a particularly big challenge because if you just feed the points in the usual fully connected layer and you can permute them in any way, there's really hard to learn from this, right? Because the order can be anything, so the weights don't know where to look at because they're tied to a position, and like even convolution is not clear how to make it work. So you need some interesting architecture to solve this. And interesting architecture they have. So their building block is basically is this part. And what it says is every point will go through a bunch of layers where it's run, the same network is run for every point at the same time. So if you run every point through the same network and produce an embedding, you have a guarantee that if you reorder the points, just the embeddings will get. That's the only permittable operation. The other permittable operation is global or average pooling, right? So if you do like maximum across every dimension, all of these points, or average across every dimension, again, the permutations won't matter, right? So they're building a network just out of those elements. Another element they construct as a higher level from this is a subnetwork that also has just those operations that predicts a matrix multiply to try to rotate this point cloud to a particular position so that it's invariant to scale, rotation, and translation, right? And matrix multiply on every point also works like this, that it's immune to reordering. And they build a network just out of this element, and surprisingly, it works for real data. Like even though you can't use all the power of deep learning, but just some of the permittable operations, still, all of the previous results are from using this architecture. And there's, I recently learned that people use this in Kaggle competition on like related to cars when there's like really a point cloud and you don't have ordered planes, so they do get a variation of the point net. So I'm not going to go into this detail. This is a paper from Twitter on super resolution. The interesting thing they wanted to use this to highlight is the conference world is kind of has the collision with archive and preprints, where the conference deadline is basically half a year or more before the conference happens, and everyone sees all of the papers from the conference half a year before. So you're here and they talk about the exciting paper that half a year ago they're like, you've seen it on Twitter, you talked about it with your friends, you know everything about it, and then there's a paper about super resolution from Twitter. It's a cool paper, but it's just like old news by that point. Interesting variation of this, again, I'm not going to go into the detail. It's also a super resolution, but for the extreme JPEG compression. So they try to reconstruct a regional picture based on like a very, very low quality JPEG, and are able to use the structure of JPEG as an additional regularization. So basically knowing that the source image was produced by JPEG compression helps in super resolution. Again, minor point, but it's like cute. So the rest themes for me are like minor, and I'm just going to briefly glance over them. There's additional work for trying to interpret how deep learning, how deep models work and what neurons learn. Previously, we always thought that it's interpretable. Those neurons, even at the higher levels, they learn high-level concepts that it's hard to explain what they are. And through some additional data, they showed that for a lot of the convolution architectures, significant fraction of the neurons, like 30% or more, can be explained, and they seem to be looking at the very specific things, which is a kind of interesting discovery. As usual, with interpretation is hard, so you could question the results of this paper, but I mean, if you're interested, check it out. Continuing progress on compressing models for like embedded, mobile, and stuff like this. Nothing super out of the ordinary to report, just like continuing small, like incremental progress. What else do I have? This is it. Oh man, there was like a very cool image here. I'll try to refresh one more time, just in case. And this gets us to the end. Let's give the internet one more chance. One more chance. One more chance. Maybe if I scroll there fast enough, you will learn that this is the image too. This is the image at the end. I guess you can't do it. All right, so in the end, obligatory part that we're hiring, like instrumental, jump on that rocket ship, all that. The one bit I wanted to insert is we're hiring for people in like computer vision and machine learning, but we're not requiring you to be a PhD in either of this. We're totally open for someone to learn, and like if you're just interested and kind of really into the stuff, please talk to me. That's it. Thank you. Other questions, like requests for further explanations, anything? Okay, we're good. Oh, no, all right. Questions, yes, please. Yes, yeah. I'll share this, and it will load all of the pictures. And there's a bonus for you. Another question?
Any presentations that caught your eye from manufacturing perspective? Stuff that you work on?
Say it again.
Are there any presentations that caught your eye from manufacturing perspective?
Right.
Stuff that you work on?
Yeah, that's a great question. So our setting in general is we're trying to get images from the factories because it's a very rich information and try to detect interesting things there. And one thing that kind of captures the kind of is plainly obvious is how big is a disconnect between topics interesting in academia and topics that are interesting in practical terms. For example, we have a super high resolution images for like 25 megapixels. There's nothing that talks about how you classify, like detect and other stuff on these images. Like everyone's like, yeah, 224 by 224 is like, you know, the images that are like 300 by 300, and there's like practical difficulties there. Another one is, so our product is doing something very kind of practically important called anomaly detection, as in figure out what's like very different without any prior data in the samples. And this problem is like overlooked by academia completely. There's 2 or 3 papers related to like novelty detection, and it's somewhat disconnected from deep learning, and people are just like, there's, you know, 1 or 2 students in China that look at it a little bit, and there's like a huge practical importance for this problem because it's not clear how to apply it to deep learning. What else? There's a separate part of CVPR that's relevant to us about cameras and industry and stuff like that. I wanted to say that on the whole industry expo, there was one and only one company that works with manufacturing, which is interesting because like computer vision is a big part of it. And again, this just speaks to the kind of disconnect and like opportunity there. Yes.
Based on what you said, maybe you could start a new sub-branch called industrial deep learning.
There's companies in this space. Yeah, it's happening right now as we talk about it.
any video classification?
Right. Yeah. Great question. So fair amount of work on video, just because it's not that interesting to me. I didn't look at it in the detail. There's a lot of exciting work at detecting parts and like key points on the human and pose recognition from the videos that's consistent across the video stream. You might have seen some videos online, so that's like, it seems like there's a significant step there. In general, I kind of feel that video classification still falls in the same themes. People think a lot about how to make it work with less labeled data. You think about how to combine video and sound and all of this information to make it work better. I guess that's all I have to say about this. Yeah.
We did talk about, ImageNet data set has been there for 5 years.
Yeah.
Million images. Computing and the network size has grown like so much from like EGG to less than Did they talk about a data set, which is better than ImageNet?
Right. Right. So there was an interesting talk by Fei-Fei Li about kind of recap of the story of ImageNet, and basically it ends with, I think we're close to extracting all of the value there is from ImageNet, but the history tries to, but history tends to surprise us. Like no one knew, like no one thought that like you can break 99 on CVPR, right? But it seems that you can. So I think and in this year, for example, there was a surprising boost on the ImageNet recognition challenge, which was more than the year before, for example. So I think we could be surprised, but the general kind of feeling is we need a new set. There was a big video classification data set for short tasks, which again I think was released like half a year ago, but like it was a CVPR paper. But the general thing is we need new, either larger or more interesting or more specialized data sets. Another way you're saying is, how every paper claims state of the art on something. This CVPR, you almost can't look at those results because everyone is doing some separate data set for their own tasks. Because like the main just straight up recognition and straight up detection is so saturated. So we're like, there's a clear trend, at least on CVPR, branching out in a lot of different tasks as opposed to like being ImageNet to death. Yeah.
Kind of a side comment. So recently on the survey, focused on images and last year somebody's doing audio.
Exciting development.
And scary.
Well, all of the stuff is pretty scary. This is not for the weak of spirit. There was a question?
Yeah, I was wondering if you could give a better summary of the differential rendering that they use in synthetic data.
Yeah, let's see if my image is loaded.
Approximation also?
So, okay. Internet, that's all right. Maybe you can combine. We'll see like the particular image. But the TLDR is the renderer is pretty simple. It's just drawing textured triangles with like a simple lighting equation. But the exciting part is they can backpropagate from the pixel change into the vertex position change. Does that make sense? So they can do like this end-to-end. So their rough architecture is network looks at the picture, comes up with the few weights of the sample faces, so it's interpolation of the faces, which are used to create the geometry, which then is used to draw triangles and textures and stuff like this. And on the pixel losses and pixel difference, they're able to backpropagate all the way to the coefficients of the faces and the texture pixels, like the pixels of the textures that the network predicts.
So does this generalize the block-based analysis object detection, which is based on rectangles? Things called fast-fire and faster.
So how should I put it? I think it's somewhat separate, and like the cool part about this is we're able to generate a completely new image based on the network output and propagate a signal of how better to change those parameters so the generated image is close to a photo or something we're training on. Yes?
I understand how point net works, but basically what do they do with the input points?
So it's a long architecture where the only operations permitted is you either feed a point through a network that only receives one point, so like point position to embedding or embedding to embedding, or do global pooling or average pooling on all of those embeddings. Images.
But what is the network that what is the network that makes the point embedding?
Right. It's just basically a small number of fully connected layers that run for every point.
From 3 roots, from 3 coordinates of the point?
Yeah, so the first one is just 3 coordinates of the point, but it could produce a larger embedding, right? That the next layer will work with a larger embedding. And so it could, like, basically, yeah, so the first one is just XYZ, but it could detect features like maybe it's like closer to this side or closer to this side to a larger embedding, and the next one would work with that. And then you can do maximum around embedding, like of those embeddings that you can pass as additional context. Like for example, using this, it can find the rightmost point easily, because it would write into one of the embedding dimensions just the x coordinate, right? Then and like some number of like on the point. Then you can do max, right? And this will give you the coordinate of the rightmost point. And maybe you can use this down the line to construct a matrix that would rescale, for example, right, or something like that. Wrong image. Yes. No, yes. Yeah. So every thing like this is basically 3 layers, and this is 2 layers with 64 hidden units. That's what the notation means.
What is the input transform?
So input transform, those are like 3 points, like those 3 coordinates. And this is like a little network that internally here it's the same architecture with mapping and max pool that in the end produces a matrix multiply, and every point is multiplied by this matrix. So here it's also 3 points. So the whole point of the transform is a learnable matrix multiply that should like rotate or scale or transpose the points to a kind of canonical representation. Yeah, the question from the back.
Working with 3D images that are objects that are very asymmetric, it seems like it's going to be extremely difficult to be able to classify them. Depending on the perspective that you see, it could throw you off completely. So do they start like with a set of representations of different views?
No, so they classify from a single point cloud. So in the training data, they might see them from many angles or many positions, but the network just receives one point cloud and is able to classify. I want to say, like, so I should say that there is a follow-up work by the same group, which was not on CVPR, but it was published before the CVPR started. It's called PointNet++, which they try to introduce partial pooling based on spatial position to give more representational power to this network. Yes?
Thanks, so I'm more interested about the digits labeling the unlabeled digits. So you were showing the image that you were comparing, like, let's say forks. So they are going from labeled forks to unlabeled, and then going back from unlabeled to labeled, right? And we are comparing them based on the code. So isn't there at least we know that this unlabeled 4, that we are thinking that it's 4, is going to go, there is at least a chance that it's going to go back to the same 4 that it came from.
Yes.
So is the 4 that was originally used to...
Yeah, so they have a special...
Is still kept in the labeled data, or it's removed and it's replaced with let's say, other form.
Yeah, so they explicitly not let you to come back to the same one that you came from. Yeah, it has to be for this whole thing to work.
There's an X chance.
Yes. Yeah. And they also have to reshuffle the batches in a special way. So there are examples like this, right? Like for this to work, it has to be that there's 2 4s in the same batch. Sure yeah, so they have a special reshuffling, which has practical limits. Like for example, if you have 1,000 classes or like a lot of different classes, it might be hard to pack enough of the similar examples in the same small batch. But yeah, it's a constraint for this method to work. Question over there?
Yeah, I'm curious if you have seen any treatment related to robotics, for example, in machine that people are using graphical models to model objects to solve it in object models.
Yeah, good question. So generally, CVPR is not strictly a robotics conference. So I think they talk a lot about vision tasks that happen as part of robotics, but not necessarily the kind of the end-to-end manipulation things. So you don't hear a lot of that. There's still some visual recognition tasks that people approach with deep learning, and I didn't mention them because like there's a lot of them and not like really groundbreaking results. But for example, there is this question of simultaneous localization and mapping, so-called SLAM, and the task is, so you have like a machine or something in a unknown environment that you can look at through the camera or LiDAR or something like this, and you move in this environment, and at the same time you need to figure out where you are and map the environment around you. Like some models of Roomba do this. The higher-end models of Roomba do this. And it's a traditional computer vision problem that runs to an embedded system, and there's like the traditional computer vision pipeline to solve it, and people try to embed learnable pieces in part of this to solve like specific either subtasks or this end-to-end, which is absolutely one of the applications is robotics. But people don't talk as much about kind of this end-to-end manipulation things. All right, thanks for the questions. Great questions, great follow-ups. Really enjoyed this. Thanks for being here. Right. You disconnect.
Thank you, Simon, and you guys have been a lovely audience. Just take 2 more minutes and do the draw for the SU World tickets. Simon, I'd regard you to pick up.
Oh yes, all right.
Thank you.
Okay. How many? One time? 2. One at a time? Okay. Tickets. The numbers are 3856298.
385?
383. Last 3. 298.
Got it?
Nice. Nice.
We'll take pictures of that.
Okay, cool. All right, okay. I'll do the like the proper shot. So it's not from the top somewhere.
By the way, my name is Pradeep Kumar, and I work for the U.S. Army, and my application is Anomaly Detection.
All right.
For image-based to find if a particular population has kids or children or pardon? Yeah, to be able to detect if a particular group of people has civilians or non-civilians or objects of interest. So if you have a group like this, we want to be able to detect what is a person of interest or if something is missing. So in a UAV application, this could be useful to prevent casualties to civilians.
Nice.
Did you pick a ticket out?
Yes.
Great.
It's 325.
Last 3.
All right. Okay. So close. So close. I don't know this guy. Totally not a scam.
Simon, you want to take a picture with it next to the H2O?
Just anything.
All right.
Right.
Thank you, everyone. Have a good evening.
It was a great talk.
Thank you.
So I have a question about H2O. Sure. I'm looking at all the different models it provides. It doesn't provide SVM. Do you think they will, or does it just not?
Sorry, I didn't have the question.
The H2O I noticed doesn't support SVMs. Packages. Do you know if they will someday, or is it just not on their radar screen? Or?
I'm not too sure, but I don't think that's in the roadmap for anytime soon. For H2O World. So for students, there's no discount code, but the ticket is priced at $99. You just have to show up with your student ID card at the event. That's what the process is. Yes, so when you go to the H2O World website, just Google H2O World. The first thing to link that pops up is ours. And when you click register, there'll be multiple options, and if you select the student one, the ticket is priced at $99. There's no condition, no promo code to that. Just bring your student ID card at the event, and that's all.
Right. And if you apply their, what's going to happen if you apply
Kumar.
is probably will find similar objects to the one that you're looking in the image net. Right? And it will still need to classify based on the same 1024 in 1,000 other images. And the fact that there's just 1,002 does not, it's by itself is not a big problem. What could be a big problem if, imagine that you use all of the images, and there's 1 million of their images, and like tiny fraction of those, and that would be a problem. But if, say, half of the images are even the training images.
Oh, there you go. Okay.
And half of you get similar images from ImageNet, right?
So you're recreating the layer from scratch.
No, you still start with retraining. You still start with retraining, but you train not just the
entire set.
Not the entire set. Some samples of the source. And if you like like those two are still important because they determine half of the loss, right? Like because you don't care about what the other user is, right? So it's still very important to like those two are much more important than 1,000 other things.
So what's that ratio?
Yeah, I think they did.
That makes sense because I was thinking you trained only on the new data set, which is the 2,000.
Some part, yes. No, I think it depends on how similar your data set to the source. But since they select things that are similar to the better low-level features, usually there's a lot of like low-level features are very similar patterns, similar text.
How do you do the selection? Like a Gaussian distribution of
No. So they take a complete network on their source, and they acquired the histogram of the activation of one of the early layers, like 2 or 3 of like LXNet that you can use to train you on. Should be similar to the same histogram from the source. And then there's flows that you have like a very it's not like they selected the main they select their like there's still plenty of features to make it stay this not but like in general these things are like you look for ideas to try.
Yeah, absolutely. Yeah. Well, thank you.